Hello, my name is Enzo Hines. This is Physics Lab 2, Motion of a Falling Object. The purpose of this lab is to measure the position of an observable object falling and analyze the forces acting on it to lead to its acceleration and movement. Physical principles used in this lab are Newton's second law to determine final position and the formulas of force of gravity and force drag. The main result of this lab was being able to observe how the observed motion of an object compares to the computational model of just the objects with the effect of gravity and the object with the effect of gravity and drag. This allows connection and calculations to be made about net forces through Newton's second law. Newton's second law is a law that relates net force as a product of mass and acceleration. Since the mass of the ball does not change, net force is directly proportional to acceleration. The two forces acting in the y direction are represented in the free body diagram in the bottom right, and the two equations are represented at the bottom of the page of Newton's second law. Force gravity, represented by the first equation, Fg equals negative mg, and force drag, represented by the second equation, are two forces acting on our object in this experiment. My system was the packet of gum that I dropped, and the surroundings were the earth exerting a gravitational force and the air exerting a drag force. The initial velocity of the gum packet was 0 meters per second, and the initial position of it was 0 along the y-axis. I defined movement towards the bottom of the screen as the negative direction on the y-axis, and defined the origin at the center of the gum packet. The experiment began with an object being dropped from at rest position. The camera was set up at a steady perspective to watch the movement along the y-axis. The video was then imported into the tracker and points of mass representing the object center were marked. This allowed the software to determine the change in position of the ball over time. The same initial conditions were inputted into computational models in GlowScript. Two computational models were constructed, one with just gravity as a force and the other one with drag and gravity. The two positions over time were graphed with the observed motion to compare them. The starter code was used. Initial velocity and position vectors, object mass, and change in time and radius of the object were inputted into the GlowScript code. Equations for the force of gravity and the force drag were inserted to correctly account for the net forces along with the velocity and position update formulas in lines 69 through 79, and the force negative vector was edited to be the difference of Fg and Fd, as seen in this slide. Here's the code that I edited, including the equations and the initial conditions. Here's the position of the gum packet over time, as the observed motion is plotted in purple, the gravity with drag motion is plotted in blue, and the gravity only motion is plotted in green. As you can see, this point where the observed motion stops is where the ground is. There's many possible errors that could have arisen in this lab. The observed motion of the dropped object differed from the drag and gravity model that would supposedly best model the motion of the object. This may have arisen from some rotational energy or slight movement in the x direction that could have changed the velocity of the object. The incorrect drag value may have been used, which may not be the actual b value of the object, which could have led to the difference in distance. When comparing the three plotted motions of the object, it is clear that the computational model with the force, drag, and gravity was close to the final position of the observed motion. It does seem that overall there was less net force acting on the object than what was predicted in the computational models. This means that the force of drag was larger than predicted. Percent difference calculations were made between the observed motion and the two computational models. Here, the observed motion and just the model that plots the force net as gravity, there was a 65.7% difference between the two models. And with the force with gravity and the force drag, there was 28.6% difference from the observed motion. Net force cannot be calculated over the entire interval because as the velocity increases, the drag force increases, which would lower the magnitude of the net force. So there's no constant force. From Newton's second law, since the mass of the object is not changing and the object is accelerating, there must be a net force at play. However, the object is not accelerating at negative 9.81 meters per second, which means there's more than just the force of gravity on the object. If the object was initially thrown downward instead of being dropped, as it was in the experiment, the terminal velocity would be different. When plugging in an initial velocity, the object would continue to accelerate at the rate of the acceleration, which is modeled by the force net over mass, where the force net is the force of gravity minus the force drag. However, it would be starting at a higher velocity. And this is shown in the computational model. When the velocity begins at a non-zero value, in comparison to the velocity starting at 0, it ends at a larger terminal velocity than it started from when it would have been at rest. From the models that describe the motion of my object, there's a model that indicates that the force of gravity and force of drag are equal. The force of gravity on the object is calculated by the mass and the gravitational acceleration constant, which is 9.81, and the mass was 0.014. This equal to a product of negative 0.13734 newtons of gravitational force on the object on Earth. And this value has to be equal to the force drag, which must be equal to 0.13734 newtons. This would make the force net 0, which means that the object would not be accelerating in any direction.